Okay, we had a really good clap clap. The clap clap means okay, so a few quick things and we're going to jump in today. My brain is lost today. Focus. Okay, so your grade is pretty much set. It's not going to change unless you have any last minute things you want to scrape a few points out of. At the end of today's lesson, if you want you can turn in your smiley faces to get some extra credit boost. If you don't need to use them, then you get to save them and they roll over to next term. Okay? So, with that. With our new units, we're jumping into Unit 3. Like I said, everything from here on out is just going on the next term. We just aren't going to waste days because we don't have them to waste. Unit 3, just to kind of give you a preface of where we were and where we're going. Okay? So Unit 3 in simple terms is all about solids, liquids, and gases. Now, very simple topics, right? You learned about them even in elementary school. The difference here now is we're going to dive very deep into all three sides of the chemistry triangle. So we'll kind of be just diving really deep into what makes something a liquid, what makes something a solid, what makes something a gas, the mathematical relationships that we'll be doing with them, a lot of different things. Unit 3 is a little bit bigger. If you haven't noticed already, the note packet's a little more pages than our last one, meaning we will be spending more days on it. And with that, it does have a higher percentage amount on the end of your test. So units 1 and 2 are claimed to be about 7 to 9% of the final AP exam. Okay, which means like it kind of seems weird because you spend all this time doing it and then on the final it's only going to be like maybe 3 questions from Unit 1. 3 to 5, that's it. Okay, but with Unit 3 is said to be 12 to 15%, so almost double what the others were. There's more topics, so that's kind of part of it. Is there more things that can be covered? But then there's also some just like guaranteed questions that like, I don't know if you remember, sometimes Unit 2 I said this might be on the AP test, like hybridization, maybe a question, maybe won't be a question this year, just depends on our odds. But with Unit 3, there's a lot more guarantees, like there's going to be a question about this, so we don't want to not understand it well. Okay, I have your Unit 2 FRQs for you. I'm going to give them back to you at the end so we don't get distracted from what we need to learn today. But I would like your help because I can get carried away with chemistry and teaching. So if I haven't stopped teaching by, let's say, 12:05, so 10 minutes before the bell, if I'm still teaching, wave at me and let me know that I need to hand back your test so I don't forget. Okay, because otherwise I might just forget and continue on class. Okay? What?
What if someone just asks me one?
Well, that's why I was just kind of saying, one of you be my alarm.
Can't get your phone out.
Yeah. So, but I trust one of you, between all of you, will recognize the type. Okay? All right, so to get us started off today, I got a smiley face question for you. I want you to do it on your own. So don't talk to your neighbor, don't look at your neighbor, because I want your brain to think. Okay? I want you to draw me a picture from what you understand about solids and liquids and gases, okay, of what it would look like at the molecular level. Now, for simplicity's sake and uniformity, the original question on your note says water. I don't actually want you to do water anymore because there's a reason for that. We're just going to say, let's do oxygen. Okay, so if oxygen were to exist as a solid, a liquid, and a gas, for simplicity's sake, let's say this is oxygen, a circle. And you don't have to circle it if you want. Okay, so that's oxygen. Okay, if I were to have 10 of these, let's draw 10 oxygen atoms in each box. What's going to be different between those 10 oxygen atoms as a solid, as a liquid, or as a gas? Okay, take 2 minutes and in those first 3 boxes, draw me a picture. So draw 10 circles in each box, but they should represent a solid, a liquid, and a gas. Okay, I'll give you 2-ish minutes to draw that. When you are done thinking, set your pencil down so I know you're done. While you're drawing that picture, I'm going to come put some models on your desk. Do not touch. I'll let you touch them in a moment, but don't touch them until I say so. Okay, resist the urge because they look really fun, but don't touch them yet. Okay? Okay, no talking. On your own. Use your own brain. If you're done, then just ponder life silently in your head. I know, they look so so fun, but don't touch them. What piece of instruction?
I'm not supposed to instructions.
Don't touch. Don't touch. I know. I'll tell you when. It's like 2 more minutes. I know, but still don't touch. With that little kid thing she was eating.
The only way I would survive is no, I'm water
Don't touch.
I did. To be fair, that was at my leg. Is that food in there?
I'll be Does this count?
One of those kids. I'm not touching this, Mom. I'm not touching this. Okay. Take your hands for me, everybody. Put them in a fist. Okay. If these fists represent oxygen, everybody show me how your solid model looks. Okay. Show me how your liquid model looks. And show me how your gas model would look. Okay. Very good. Have a smiley face if you went like this. Okay? It's so crazy to think about how at the molecular level, the difference is just distance and speed as well. We can't really draw it on a 2D picture. But that's really the only difference between a solid and a liquid and a gas is how close the molecules are and how fast they're moving. Outside of that, though, with our eyes, like if we go to the chemistry triangle, there's a huge difference with our eyes between a solid and a liquid and a gas. Right? Like I can swim through liquid water, I can't swim through solid water. I can't really even, I can walk through gas water. Sounds weird. Okay, I can walk through it, but I can't make myself swim up like I can in liquid water. Right? Like it's so different on the big scale, but at the small scale, it's just proximity. Okay, so here's my next question I want you to ponder. I want you to answer on your own first once again, and then you'll get a chance to share. Okay, if the only difference between a solid and a liquid and a gas is distance and speed, okay, now we'll talk more about this in this unit, but for those that are unaware, temperature is the measure of molecule speed. So when we're measuring the temperature, it's indirectly telling us how fast they're going. So if two substances are at the exact same temperature, let's say water and carbon dioxide. Okay, carbon dioxide's in this room right now because we breathe it out. There's probably some water vapor in here too because there's a little bit of humidity. Okay, but normally what is the state of water at room temperature? Liquid, right? So why would water exist as a liquid, but carbon dioxide exists as a gas when they're at the exact same temperature? That's the next question right below your boxes I want you to ponder. Now as you ponder this, you are now permitted to touch your water molecules to help you maybe come up with an idea of why. Don't talk to your neighbor though. Just play with them and think to yourself. Okay? and come up with a conclusion of why is CO2 a gas while water's a liquid when they're at the exact same temperature. Okay? And keep your explanation here, keep it simple. Okay, think of if you're explaining it to like my 6-year-old. Okay, what must be going on that causes that difference? Alright, now as you continue to play with the water, make sure you put it down for a second to write your answer down. We'll keep playing with them as we go through the lesson today. Don't get too distracted from the target we're trying to hit.
I said it's because water's a large molecule. It has
Okay, give your attention this way. This really, guys, is like the fundamental theme to the entire Unit 3 of understanding this idea that's so simple, but it's so powerful in what's going on. So anyone by raise a hand have an idea they want to piece together for us? Dylan, let's hear it.
Because it's polar.
Give me more.
Like, it's polar, so it sticks together, and maybe is CO2 polar? I don't know. But, like, maybe it's not polar, and then it doesn't have any attraction.
So from what Dylan's saying, Dylan is saying we know that water is polar from our last unit, which polar is going to be a huge theme in this unit. There's a big part of that here. And he said, so since it's polar, what do you notice? What happens? There's a force, right? There's a force of attraction between the two molecules. If there's a force, if they start coming together, what naturally happens? Do I have to put them next to each other to get them to link? Or do they pull each other together? They pull each other, right? If you put them close enough, one of them will jump, right? And attach to the other one, right? You don't have to like literally put them side by side. Okay, someone add to what Dylan said. So we talked about this idea of polarity. Have some fish for that. Alex, add to it.
So, I mean, yeah, it is basically just adding to that. Like, it's harder to put carbon dioxide closer together than it is water. And so we were saying, like a solid is like a lot more close together than a liquid. So if carbon dioxide is not polar and it doesn't like stick right next to each other, water molecules can be closer to each other without having to expend like extra energy or whatever trying to put it closer.
Perfect. How's my piece that? Jack, add on?
They also all the different atoms and stuff are different boiling points and freezing points and all that, so they all see the different things of
So what Jack brought up is then also connecting it to like another side of what we see with our eyes of even their properties are different, right? That water has a different boiling point than carbon dioxide does. Obviously, hence why one's a liquid and one's a gas. So really it goes down to that there must be, right? If a molecule is going to naturally be like this, versus, so carbon dioxide naturally wants to be like this. Water, naturally, wants to be like this, right? Moving still, but pretty close to be a liquid. There must be something there that's different, that's holding the water together versus not the CO2, okay? What we're learning about are these things called intermolecular forces. Forces between two molecules. Okay, I often nickname this the friendship force to keep in mind it's between things. It's not within. Okay, it's not the bond of my arm to my body. That's a true bond. It's the relationship of molecule to molecule. Okay, so that's kind of the thing. It's abbreviated IMFs, intermolecular forces. Okay, so our goal today is we're going to learn about 3 different types of intermolecular force, and we need to be able to label which type each molecule has. Okay? In reviewing, all right, so I need everyone to take their water, set it up at the top of your desk. I'll let you play with it later, but sorry, I don't trust you to focus at the same time. Okay, there you go. Put it in your box so you really can't touch it. Should have done that the first time. Okay. All right, so in reviewing this idea of an intermolecular force, we do want to talk about briefly though about metallics and ionics, because they don't experience intermolecular forces because of the way the bonding exists. Okay? In water, water is covalent, right? The bonding is happening between this O and these two H's, and that's it. In a metallic bond, bonding is happening like everywhere because of that sea of valence electrons. And so that's the type of force that happens in a metal is just metallic bonding. Okay? So what we're going to do is just as a quick review is we're going to remind ourselves of the properties of metallics that they have because of their structure. Okay? I'm going to get us started with one, and then we're going to pick on which row? We picked back row last time, so we'll keep so back row, you're up to that. So what's going to happen is we're going to start with Jonah. Okay, you're going to have to give me one property that metals have based on what we learned last unit. If you can't think of one, you can always pass. You don't get the smiley face if you pass. Or you can always ask a question. Questions also earn smiley faces. So when it's your turn to bat, you either have to tell me a property or ask a question, or you can pass. Okay? So Jonah, can you give us some property that you remember about metals that we learned from our last unit that can describe them? Perfect. So I'm going to write that down. Conducts electricity as a solid. Okay, Jonah, do you remember why?
Because the proton, there's a free-flowing electrons.
Yeah, that electron C just helps the current continue to flow. Perfect. Caleb, give us another one.
Malleability.
Good. And why are they malleable?
Because they're not held in place super hard. They're still like able to move around.
Yeah, right. Once again, that sea of electron isn't a rigid structure, right? You can easily shift them around and the balance is still maintained. Perfect. Have a smiley face for that. Daniel.
Not soluble in water.
Good. They don't dissolve in water. They're not soluble. We didn't talk about this one a ton, but do you remember why, Daniel? That's okay. And we'll have a whole day in a few weeks about solubility. The basic idea with the solubility is in order for something to be soluble, this little guy has to penetrate it. This can't penetrate the electron C. And so it can't get inside the bond to pull it apart. So it just doesn't dissolve. Thanks, Daniel. Have a smiley face. Gavin, can you give us another property?
Property, can I give an example?
Sure.
Okay, I guess gold.
Good. So for metals, it's just a metal bonded to itself or a metal with another metal, right? Remember, metals are left of the diagonal, right? So that's how we can identify if it is a metal is by the type of elements it's made of. Thanks, Gavin. That's my face. Liam, can you think of another one for us?
High melting point.
Good. So they typically have very high melting points. Okay. Do you remember why that is? Melting just goes about that you're trying to break the forces. And so if you're melting a metal, you have to break the electron C, pull it apart, and it's going to resist that, right? Good. Have a smiley face for that. Brian, can you think of another one? I'm trying to think if we haven't hit any yet for metals. There's one more I can think of, but if you can't, that's okay.
Conducts as it doesn't conduct as a liquid.
Oh, that's true. It doesn't have aqueous conductivity. That is true. I didn't even think of that one, Brian. Good one. Obviously, they don't dissolve, but that's not going to get them to conduct either. So good. Yeah, have a smiley face for that. All right, last three. Put your brains together. Can you think of one more thing to describe metals? I know it's hard to be at the end of the row because they keep taking what your brain's probably thinking of, huh? It does start with an L. Jack's reading my mind. It's okay. It's luster, so they always have a shine to them.
Oh.
I mean, obviously they can rust and it can be hidden. Oh, shiny. Just a different word. Yep. But yeah, that they're shiny, lustrous, so on and so forth. Okay, perfect. Okay, let's review. So now, row 2, you're up to bat. So we're doing ionics. And we're going to start with Scott.
Why?
Scott, give us property of ionics.
They are water soluble.
Good. So ionics dissolve. They have good solubility. Some better than others, but they all dissolve to some extent in water. Okay? The cool part about this, and we'll do this on our solubility day. Where's my salt molecule? So this right here, right? So this is like a salt crystal. Okay, where you have your positive, negative, positive, negative, positive, negative, right? Build it big. Okay? The reason why all salts dissolve is because these are positive and negative. And since water is polar, it has positive and negative. So little water can come in here and attach. Now imagine hundreds of waters attach, and it starts to pull it apart. Right? And so that's why they all dissolve to some extent. Perfect. How's my face, Scott? Evan, can you give us another one?
Yeah, not malleable.
Good. They are not malleable, very brittle substances, right? Do you remember why?
Yeah, because if it shifts over, the whole ionic compound, like solids based off of positive and negatives. If it shifts over, it's gonna be positive on positive and negative.
Perfect, right? Yeah, we mess up that lattice in a sense of like, I don't know if I can do it with my model, but like those don't hold together. They're no, right? Good. Perfect, Evan. How's my face? Levi, got another one for us?
Can't it conduct electricity once it's dissolved?
Good. Yes, they're very good conductors once dissolved. How's my face for that? Do you remember why?
Because does it have to do with the metal being separated?
Yep, because you need movement to conduct electricity. And so once they dissolve, these are now apart and floating around in space, and that can thus send electricity through it. Perfect. How's my face?
Well, they don't conduct in a solid form.
Good, but while they're a solid, not conductive. Right? As a solid crystal, they do not conduct electricity. Why not, Dylan?
Because they're not moving.
Yeah, lack of movement, right? It's a very rigid structure. Perfect. Got another one for us? I'm trying to think which ones we haven't hit either. That's okay. You can pass.
I passed.
Emily, can you think of one we haven't hit yet?
I know this one.
Good. Oh yeah, there's one. So they have really high melting points. Do you remember why, Emily?
Because
That's okay. To melt, what happens at the molecular level if this is going to melt? Yeah, you got to spread it apart. And if to spread this apart, you have to break all those negatives and positive forces. So it just takes a lot of energy to do that. Lindsay, can you think of anything on a hit? Good one. Yeah, so ionic is a metal with a non-metal or any combination of it, right? You have many or doesn't matter how many, but if you have any combination of metals with non-metals, it always makes it ionic. Perfect. Lindsay, you have something for that. Okay, so last unit covered ionics and metallics. The reason why we had to skip really the covalent properties is because we have to learn about what we're learning today to understand them. So we have two different classifications actually for covalent relationship. Now with covalent, it always is still non-metal, so non-metal with non-metal make a covalent, that holds true. But their properties, as we saw if you remember from our unknown bonding lab, it can vary. Sometimes they're malleable, sometimes they're not. Sometimes they dissolve, sometimes they, they do both, right? Sometimes they melt easily, but there's actually a few cases where they have really high melting points. And the reason why is because of what goes on with the covalent substance. The difference here is, in one single molecule of water, that's a very strong relationship. But the relationship between a water and a water isn't a real bond. It's just an intermolecular force. So depending on the type of intermolecular force then changes the properties of them. If they hold tighter, well then they're probably going to have a higher boiling point. But if they don't hold very tight, then they'd have a much lower boiling point. But it's all, you get great variability because of it. Molecular covalents are small molecules held together by intermolecular forces. This is like a rough Miss Alviso statistic, so if you go look this up and it's different, let me know. I'm just kind of making this up to help prove a point. But 99% of molecules that are covalent are this kind. Small molecules held together by intermolecular forces. The 1% of covalents that aren't are known as a covalent network. Covalent networks are still covalent, but they almost bond in such a big way it seems ionic. A great example to remember when you're trying to what's a network? Think of diamonds. When diamond bonds, it is pure carbon, so diamonds are just straight up carbon, bonded in 4 ways, but then all connected. So it'd be like, I don't know, I'm making this up again. Imagine if we all had 4 arms because we're carbon, and then everybody grabs the person behind them, to the side of them, up and down, and then we just all connect the entire school, that's a diamond. So it's massive network, covalent network of bonding.
Would most like jewels be like that?
Not, so other jewels outside of diamond can sometimes have a similar idea to it, but often they're actually ionic, which then still also has that massive idea. So with that, going off that idea though, what would we predict if it was a network? So our other properties in the box above, just put they vary, because they vary so much and we'll get into their details later. Networks are a little easier to identify because of what's going on. Anyone want to make a prediction of what type of properties a covalent network would have with any of them? Go ahead, Bryson.
High melting point.
Yes, extremely high melting and boiling point.
That's my diagram.
Why, Bryson?
Because there's just so much.
Yeah, you're literally having to break the bonds. When I melt ice, am I breaking a bond? No, I'm just moving the molecules apart from each other. But like if you try to melt a diamond, you have to literally break the actual chemical bond, which takes crazy amount of energy. Good, how's my feedback? You got
Like not brittle at all.
good, yeah.
Super hard.
Or yes, very, very hard, right? And as often we might know, diamond is like the hardest substance on Earth, right? And it's because of this crazy connection that it has. Now this other picture right here is another example of a network. This is what you could say is maybe like a linear network. It's also carbon, so it's straight up carbon. Carbon forms networks often. But this time it only connects across. Between the layers, it does experience an intermolecular force. So between this, it's very weak, but within it, it's extremely strong. Does anyone know what it might be? It's also pure carbon. Gavin got it. He's pointing to his pencil. It's graphite. So in your pencil is graphite, right? It's not lead, even though we call it lead. Okay, does it say it on the paper?
Yeah.
No, well, I don't think Gavin looked there. He just knew, right?
No, I don't.
Oh. Just trying to be good at it. So when you look at your pencil here, so the way a pencil works, right, is you have layers of graphite on top of each other. When you write, you are laying down the layers, and that's what creates your line on your paper. The individual sheets themselves are crazy strong. Between the sheets, though, are just intermolecular forces. So actually, like if you get down to a single sheet of graphite, it's a really, really strong molecule. But between them is very weak because it's just an intermolecular force. Questions on what a covalent network is and understanding the difference? Now, if you have to assume something, don't assume covalent network, because most things don't do this. In terms of the AP exam of like, well, how do I know if something has it? What I've seen from past years in studying it is they're going to give you information like a picture so that you'll know. The only other way is just to memorize the covalent networks, which like, don't do that. That's pointless unless you just really want to know them. But
They're like not very much.
there's not very many, yeah. But in the end, every AP question I've seen that's about a covalent network, they give like an image, and from the image you should be like, that's not a normal covalent, that's a network covalent. So, okay, let's get down into now our three types of forces that happen, okay? So, intermolecular forces, as we said, describe the force that exists between two different molecules. Okay, so keep in mind it's the friendship force, the force between this and this. We always represent it as a dashed or dotted line because it's not a true bond, right? We do solid lines for true bonds, which the fancy name for a real bond is an intramolecular force. So inter is between, intra is within. That doesn't really matter if you know that, but in case you're curious. Okay, but keep in mind that it's, once again, the between thing. So sometimes, a lot of the times when we talk about intermolecular forces, the problem only shows one molecule. But you should always take into account what I'm trying to describe is the relationship that this molecule would have with another one. Because really, if you really only have one molecule and isolated just one, there's no forces, there's only one. Right, so we're always visualizing two of what they're asking, okay? All right, the first type of force that exists, not first, I guess the first one we're going to talk about is known as a dipole to dipole force. Okay, dipole to dipole. What does it mean if a molecule has a dipole? It's polar, right? So it just means that there's a shift in the electrons, right? You have that arrow, the dipole arrow, and it results in a negative and positive sign. So this right here is like our electron density map, our red and blues that we drew last unit, okay, to show a dipole moment, right? A polar molecule, where this side has become negative, this side has become positive. Why do I know the arrow's pointing this way? And how do I know they're going this way? Electronegativity, right? So everyone has a higher electronegativity. So this is HF, is the example I picked. So since fluorine has a higher electronegativity, it's going to pull the electrons towards itself, making this side negative and this side positive. Okay? The dipole force is just describing the interaction between two polar things, because if this side is negative, it will be attracted to another one that has a positive end. So dipole to dipole force. Okay? With your waters, you can go ahead and pick them up for a moment. Okay? If you didn't try already, try to connect two white sides together.
I did it.
I did.
You broke it. You can't break the water.
I didn't. It's fixed.
Boom. Or if you try to connect two of the red sides together, you can feel a repulsion, right?
Yeah.
Ephraim, no.
Okay? So these little models that they made are to represent that force of attraction.
Really see that.
No,
Okay? Okay, go ahead and put your water away for now. Put your water away. Okay, put your water away for now. Oh yeah, it's cool when you start making like snowflakes.
No.
See if it's better. So with this force, there's one box on there that, if I were to compare two things, and it's like this has dipole forces and this one has dipole forces, which one is a stronger dipole force? It really just depends on which one has a greater shift of electrons, right? So the bigger the dipole shift, then the stronger that force will become. So that's what that last box says. One box that isn't filled in that I want us to think about, don't say it out loud, but think to yourself. So what kind of molecules would experience this force? What is a requirement in order to experience a dipole to dipole? Don't say it out loud, think for a second. Okay, write it down if you have an idea. But what would be a requirement in order for something to experience a dipole? If I give you a molecule, what would be a test? Like, okay, this molecule must have this if it's going to have a dipole force. Raise your hand if you have an idea. Allie, let's hear it.
Oh, I was just thinking for what molecules experience this force, are you saying like specific ones or just like
Either or.
I was just saying probably what they have to have is they have to have like one side being the positive and the other charge like.
Exactly. No, you're dead on. How somebody do that? They have to be polar. If it's not polar, it can't have a dipole to dipole force. So that's going to be the test. Is you have to look at the molecule and say it's polar, and then you can say it has dipole forces. If it's non-polar, can't have this force. Hence why in Unit 2 we had to learn how to identify polarity. If that's something that you're like, I can't do that, come see me because we've got to get it figured out, right? Like if I throw up a molecule, you should be able to say, oh, that is polar or that is not polar. Which so far from what I saw from the FRQ, we're in a pretty good place, so I feel good about it. Okay? Okay, the second type of force that can happen, so dipoles if something is polar, but there also must be a force that explains non-polar things. Because even non-polar molecules turn into liquids. And if they turn into a liquid, there must be something pulling them together. And so this is explained through what's known as a London dipole force. Okay, London was the guy's name who, not dipole, I said they're on London dispersion force, my apologies. This is what I like to call is a weaker version of a dipole. So it's still this idea of a shifting electrons, a positive and negative relationship, but here's the difference, okay? So imagine here I have, you guys don't have to imagine, I'm going to show you a picture. Don't you imagine? Look up here at my model. Okay, so this is a non-polar atom. Let's call it helium. Okay, helium is non-polar, but if helium were ever to become a liquid, which it can at extremely cold temperatures, there must be something pulling it together. So the London dispersion force happens when you have a momentary shift in electrons. Keyword is momentary. In a dipole, it's permanent. They're always that way. But because electrons are always in motion, it's a game of probability, right? Like if I were to have you all stand up and just start running around the room as if you were electrons, okay, and then I said pause, is there a chance that at one point in time there could be more of you on this side than on that side? Yeah, probability, right? So at that moment in time, we've created a temporary dipole because one side is more negative than the other. So when it happens, it turns from this into that. Well then, this now has the possibility to not only to then even influence the thing next to it. Because negatives do what to negatives? So then this becomes that. And we get, that's your London dispersion, is the force between them. Now what's the main difference between this relationship and that relationship? What's the main difference there, Kenzie? Is it temporary? It's temporary, right? This is being held, the electrons are being held over here always. These electrons could easily shift the other way, or shift back, or shift down. There's nothing that's like permanent about it, hence why it's the weakest of our forces. But it still happens. Allie?
Something that would cause London dispersion?
So pretty much anything that has electrons can experience a London force to some extent. Because at some point in time, the electrons can shift and cause it to then interact.
Is it kind of just like off of chance in a way? Like that they just
Somewhat.
start shifting in a way?
Yeah, just the probability. And then it is like, it can be a domino effect, right? Where if one of them does it, it then can send the next ones to do the same thing. The idea of the electron cloud changing is known as the polarizability of the atom. The more polarizability, which means the more shift of the electrons, then the greater the London dispersion. One of my college textbooks, it was my favorite definition of polarizability. They called it the squashiness of the electron cloud. This is my college textbook, the squashiness of the electron cloud. Does everyone see why they would use the word squashiness? Yeah, because it goes from this, and then the electron cloud gets squashed as it all shifts. Did that answer your question, Allie? Yeah. Okay, questions on, I didn't quite hit it, but obviously the more negatives you have, the stronger this force can become. So actually really big molecules with tons of electrons actually have really strong dispersion forces because they have so many electrons that can shift.
So obviously you said with helium it'd be like extremely cold temperatures to turn into a liquid. So it's the cold that causes this.
No, the cold just brings them close enough together so they actually have a chance to interact. But the electrons themselves are still what's causing the movement. Does that make sense?
Just chance.
Yeah, yep.
Great.
Yep. But it happens because we know they turn to a liquid. But like with really big ones, like for example, like iodine only has London forces when it's a pure substance because it's I bonded to I. But it's a solid at room temperature. So those London dispersion forces are actually so strong because of how big it is and how many electrons it has that it actually exists as a solid. But then you can see in the halogen family as you go up, as the molecules get lighter and smaller, this one is naturally a liquid, and then the top two are naturally gases. And so you can see that force getting weaker and weaker as the molecules get smaller. So, yeah.
What's the difference between the blue things and the rest of them?
So the blues are the ones that exist as liquids at room temperature.
And then reds are
Reds are gases and blacks are solids. Yeah. TC's like a weird mystery of like, so all the white ones are man-made, and TC's so weird of like, why have we not found that on Earth?
So like a period exists.
Yeah, but like we haven't found it.
Oh.
I want to know where it is because I feel like it has to be somewhere. Yeah, it's kind of weird. Okay, last type of categories we have dipole-dipole, which is for polar molecules. London dispersion version is anything with electrons can do it. Now these things are additive. Okay, so if something has dipole forces, it also has London forces, because everything has London forces, because it just has to have electrons to have them. This is the third one, which, so it kind of goes London, then dipole. Now the top one is hydrogen bonding. Hydrogen bonding is an extreme version of a dipole. It's still a dipole force, but it's more extreme, and so it makes it stronger. Now, the classifications or the requirements in order for it to work is this. Hydrogen must be directly bonded to NO or F. Okay, that's kind of the requirement of what elements, like what things will have this. Is you have to have H directly bonded to N or F. Now they're all in a row on the periodic table, 7, 8, 9, so I can kind of maybe help. NOF is what I have to just call it. Has to have NOF. You have to have a NOF sandwich in order for dihydrogen bonding. Now, the reason why it's so extreme, okay, is it's still just a polar, so let's come to water here. So in water, who's winning the tug of war between O and H? Okay, so the dipole is getting pulled this way. Okay, now the first thing is who's doing the pulling? If it's N, O, or F, they all have very high electronegativities, and so they pull even more than all the rest of the atoms. So that's one part of the puzzle, is you get even harder tug. The second part is H. How many electrons does H have total? One. So if you pull away its only electron, what is left behind? Just a nucleus. So it's like an extreme positive. So that's why it's still just a dipole, but it's a stronger force of a dipole because you have a much bigger negative and a much bigger positive than normal. And so then this force, the hydrogen bond force, becomes even stronger. So that's good. And I think of it just as an extreme dipole. Now, I didn't obviously come up with any of these things, and I really hate, to be honest, that they call it a hydrogen bond, because it's not a real bond, right? This is the bond. It's still just an intermolecular force, but they called it a hydrogen bond nonetheless. So, questions on what it is or how I identify it? Okay, let's go through our checklist, and then we'll try some practice problems to put this all together. Okay? So the checklist is, as we're going through it, is if I'm trying to determine what type of forces are present, the first thing to remember is this is only for covalent. If it's ionic or metallic, then they just experience ionic and metallic forces. They don't experience London or dipole. Those only apply for covalent. Okay? So if I know it's covalent, the first thing to know is, well, everything has London. So when in doubt, say it has London forces, because you'll never be wrong, because everything that's covalent has London forces.
Can you just say that on the AP test?
Say that again.
Can you just say it on the AP test?
Yeah. Like if the question says what intermolecular forces something has, always put London, because it's always going to have London forces.
Huh.
Okay? I know, it almost seems silly, but I guess to make sure you know it always has it. Okay? The second category is dipole-dipole, which is based on polarity. So then the second question is, you got to determine, is it polar? To know, does it have dipole to dipole? Which also means, if they don't give you the Lewis, you've got to draw it. Because you can't know polarity without drawing a Lewis structure first. Okay? And then finally, if it has this and if it has this, then there's a chance it can have hydrogen bonding as long as there's an H directly connected to N over F. Keep in mind there has to be a direct connection between them. Okay? Alright, everyone good there if I go to the next one? Now, just to compare here, let's label this chart a little bit with the strength of our forces. Okay? So notice the brackets up there. These represent intermolecular forces. These represent intramolecular forces, real bonds. Notice the huge jump in numbers between the two. This is not to scale, right? Because it goes 2, 5, 10, like it's not spaced equally, right? So intermolecular forces end here, and look how much big a difference of energy there is. There's so much more force in a real bond, okay? To break this takes crazy amount of energy, right? Like I think the melting point of salt is like 900 something. okay? To break water, right? 100 degrees is what water boils at.
Yeah.
Because, am I breaking the actual bond when water boils?
No.
No, I'm just breaking up friends. So that sounds mean.
Oh.
They'll come back together. It's okay. Right? But like, you're not breaking the, it's true, and you move on with your life. How it goes. Okay? So notice first off that big difference. The second thing I want you to highlight here is this overlap region. Okay? Notice right here, there are times when a dispersion force can be stronger than a dipole. Even though we rank them as London dipole hydrogen bonding, there's an overlap region. When you get really big London forces, they can be stronger than a weak dipole. So keep that in mind that it's not always true that dipole is stronger than London. Okay? But then you'll see hydrogen bonding is always stronger than both. We'll come to this one on another day, the ion dipole. Okay?
What's
All
an
right.
ion?
So this is an ionic bond.
Oh.
Yeah, so this is the strength of an ionic bond, a strength of an actual, so this is like covalent network, or to break the actual, like, pull the H off the O, breaking that bond now. So, good clarification there. All right, I'm going to do these first 4 with you, and then I'll have you try the next 4 for some smileys, okay?
It's a hydrogen.
Okay, so I'm going to walk through the first one. You're going to hear the thoughts of Mrs. Alviso out loud. So here's how I would solve this problem. Okay? So the first question my brain says is I need to know what type of bond it is, meaning ionic, covalent, or metallic, because that kind of sorts it later on. Okay? So I look at this NH3, I go to the periodic table, nitrogen is a nonmetal, hydrogen is a nonmetal, and so nonmetals with nonmetals will always be covalent. Okay? When it's covalent, I need a Lewis structure. Now technically, if they give you a Lewis structure, it has to be covalent, because Lewis structures don't exist for other things. So you technically can just, if this is given, you know it has to be that. Okay? So here's my Lewis structure. So now I'm going through, since it's covalent, that keeps me within this section of answers. Because I know it's not ionic or metallic. Because I just said it was covalent. Okay? Now, I know it's not a covalent network. Why? Yeah, but one is like, use the molecule. The molecule's tiny, right? It's just 4 things. The network would be massive, massive connection all the way across, right? So I know it's not that either. So I'm gonna put X's so I know I didn't just leave them on blank on purpose, but like thought about it. Okay? All right, I know everything that is covalent has London, so yep, it's gonna have that. Dipole, the question is it polar? So since this is a trigonal pyramidal shape, I know that is going to make it polar. So yes. Hydrogen bonding, I'm looking for NOF, N or F connected to an H,
Yes.
which I hit that category as well. So this one would have all 3. Questions on how I thought through that or how I got my answers? All right, let me do another one. So this one only gives me a single element. Now keep in mind it's always, even with this one, when we're talking about forces, right, we're talking about the force between, right? Like we're looking at what relationship do 2 molecules fill. So if it's only Kr, we're looking at, well, what would Kr and another Kr, possibly what forces are present there. Okay? Now, yeah, Ken.
What was the covalent network?
So covalent network, it's really just like never going to be the answer. It's just, they'll give you a picture and the picture's just going to show like bonds everywhere. Like, or pretty much just a diamond is a network. But outside of that, like, it's just, they're pretty bare. So, but yeah, they would show like, I don't even know how to draw a picture, but they would show like massive connections. Like your Lewis structure would be just like the entire box. Does that help a little bit? Yeah, you bet.
Doesn't Kr not bond?
Yeah, so it kind of almost doesn't fall in the category because we're really just looking at a single atom. You can think of it, well, it's non-metal, so I'm going to think of it in the covalent grouping, even though
Would have
within
London
it.
forces?
So it's going to have London forces, yes. single atom, so it's not polar. And it's not going to have hydrogen bonding, and then these obviously are default no because of how covalent it is. Okay. All right, next one, zinc some metal. These are non-metals, so that tells me that this substance is ionic. So then I just skip all the boxes and say ionic and be done. Because ionic doesn't experience anything but ionic. Okay? F bonded to itself is going to be a covalent.
Yeah, man.
But obviously it's only going to have London forces because it's not polar, because it's just, you can draw the Lewis if you want, it's not really super necessary here. Because it's just something bonded to itself, which means there's no dipole, there's no shift, so you just have London, and then everything else would be no. Questions before you try the next four with your table? Force minus. Okay, ready, go. Try them out, and we'll check them here in a second, okay?
That's potassium. Potassium's metal. Oh, that's big.
Yes. And then no dipole is it. Oh no, it's then. So yeah. And then no AG. Like it's just a set, but it's metal to metal, so it's just
Wait,
I don't know about this one. This one? Oh, this one? You think? Maybe. Should we say yes?
I don't know.
You have found
Oh, wait, no. Oh, there you
Did I count it wrong?
And networks are like, they're almost like I'll have to show you the biggest mineral I've ever created. Even that. It's crazy. It's like it's big.
it's gonna have this.
I definitely want to.
Is there an easier way? Or you just kind of guess?
When it gets bigger and bigger, if it Yeah, rather than like trying to break it down like individually, just look at a big picture, like. Okay, are we ready to check if we want another minute?
I was telling him that. He was like, no, it says something. Hey! There we go.
Okay, let's go through this and check and see how we did. This is what your homework, if you haven't looked at it, looks just like this. It's a big chart identifying what type of forces each thing has. Okay? Alright, what I'd like you to do, just because I kind of saw as I walked around, but this will just help me identify if there's any misconceptions we need to address. So what I'd like you to do is I'm going to go through it, and I'm going to, as I point to the square, just give me a thumbs up or thumbs down if you like, if it has it or if it doesn't. Does that make sense? Okay, alright, so going to the first one, show me your response here. So does this one have this force or not? Thumbs up or thumbs down? So the answer should be no, 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 no. I lost which one's ionic. Is it this one? Yes! Yes! So if it's ionic, it only has ionic, right? We don't describe because ionics are straight up positive to straight up negative, right? And we don't describe it as anything except ionic forces. Okay? Questions on that one? Okay, going to this one. Thumbs up, thumbs down. Does it have London forces? Yes, good. Does it have dipole forces? Yes, because of its bench shape. Does it have hydrogen bonding? Nope. And then it should be no the rest of it. Questions on that one? Okay, coming to silver. Does silver experience London forces? Show your response. Nope. Nope. Yes. And it's just metallic bonding, so it only is metallic bonding. Right? Because the metallic C doesn't have London forces within the metallic C, it just is the metallic C. Okay? Alright, this last fancy one here gives you an example of a bigger Lewis structure than what we've drawn. When we come to Lewis structure, it's actually still quite small. Well, it's going to get way bigger than this. So when I'm looking at this, first off, you can know it's covalent because they gave you a Lewis. Right? If they gave you a Lewis, it has to be covalent. Because if it's ionic, it would just be like the big positive negative thing going on, right? Okay, so I know it's covalent, so I know it has to fall in this category. It's not a network, still too small for a network. Once again, network would just be like carbons across the whole spectrum. Okay, not like an isolated molecule. Okay, so this one should be easy. Does it have London forces? Yes, because everything does. What about dipole? What do we think there? It does have dipole forces. So when you're trying to identify polarity of bigger molecules, you can go through the process, it's quite tedious, of drawing all the individual dipole arrows. The easier way though is just take a big picture's perspective of symmetry. Is this molecule symmetrical? No. No. If I cut it in half, looks different, right? If it's not symmetrical, it must be polar to some extent, every time. The only things that are symmetrical, the only things that are non-polar and big are perfectly symmetrical. Okay? So I know it has this and has this. Does it have this?
Yes.
Yes. We would say that this has one site to hydrogen bond if you want to circle it. It's right there. Right? It has one O to H, so it has a site for hydrogen bonding. Okay? Have a smiley face for each molecule you identified correctly. Questions on Lewis structures. Guys, it's so perfect. It's like 12 Yes, Jack. Yeah, no, hydrogen bonding is the extreme dipole, and you can't have an extreme dipole if you don't have a dipole. So that's another nice thing too, is if you identify it has this, you get it. Okay, hi everybody, thanks for waving at me. Okay, that was actually, we're done. Like I finished when we needed to. We're good. Okay, few quick notes about the test and then I'll pass it back.